Welcome everybody to the seminar. It's Andrea Vaccaro from the University of Munster. We will talk about tracially complete C-star algebras, tracial transfer and structure.
Yeah. Thank you, Karen, for the introduction, and thank you for inviting me here. I'd like to thank you all also for the hospitality. It's been very nice. It's the first time for me at this institute, and well, it's been great. Please, from Zoom, let me know if I should speak louder or if the microphone is not working. All right, so for my talk today, I would like to focus on a class of C-star algebras, which is fairly young, as the title suggests, is the class of tracially complete. Yep. So should I just right here? Yep. Sure. No problem. So as I said, as I was saying, I will be focusing on this class. Oops. Complete. Okay, this chalk is not good. Let's try this one. C-star algebras. Oh, much better. So this is a class of a category of C-star algebras, if you want, that has received considerable attention over the last, let's say, 5 to 7 years, especially in the context of Elliott classification program. And they are characterized by a sort of hybrid nature that put them in between, let's say, usual C-star algebras and their topological sort of behavior. And on the other side, with tracial von Neumann algebras. So in some sense, we will see, I will introduce the definition and give some examples. These objects really share some similarities both with this word and this word. And really, the motivation why they were studied in the first place is related to some ideas to exploit techniques and methods from the study of and classification of tracial von Neumann algebras, mainly due to Kohn, to exploit those techniques to produce results, especially in classification of C-star algebras. And these tracially complete C-star algebras serve as a bridge for this transfer of techniques, ideas, and methods. So today I don't want to talk about classification. What I would like to do is really tell you as much as I can about what we know about the structure of this object, which you will see is not very much. So before I give a more precise description of what I'm doing, let me introduce what they are. So definition, let A be a unital. Oh, okay, we don't need unital here, but unital C-star algebra with non-empty trace space. So for me, just a convention for today. By trace, I really mean tracial state. So I will always work with bounded traces, which are normalized. Unitality is not really needed. I will anyway assume it to make things easier. So yeah. And so we have this object, and given the trace, define the following two norm. The two norm on some given, so for some A, little a in A, as the square root of this. And given a closed subset of the trace space of A, define the two norm associated to X of A as the supremum over all tau in X of the two norm of A associated to tau. So again, if you want to get rid of unit in the context I will discuss, it is important to say compact instead. So I'm really willing to work only for today exclusively with C-star algebras whose trace space is compact. All right, so we have tracial C-star algebras. We have defined a bunch of new norms on these objects, and in analogy with what you have with tracial von Neumann algebras, we say that a couple Mx is a tracially complete C-star algebra if, so we want M to be a unital C-star algebra. We want X to be closed subset of the trace space of M. We want, so I always talked about two norm, but in general, this is going to be a semi-norm. If we make no assumptions on A, there is no reason why each one of these has to be a norm. So it will be, for instance, when you have a faithful trace, which is contained in X. It's always the case, for instance, when A is simple. But so we have to require here that this is a norm. And finally, the most important requirement, I'll put it here, the unit ball of M in the C-star norm is complete with respect of these two norms. So the definition, of course, as I said, is in analogy with what happens with tracial von Neumann algebras. When you have a tracial von Neumann algebra with a faithful trace, you can see that the two norm induced by the trace gives the strong topology. And so in that case, you have the unit ball complete. So here we're giving a definition which is similar, but in some sense, more general. So I'll give a further definition. So we say that Mx is a factorial Tracially complete C-star algebra if on top of everything here, if moreover X is a closed face of the trace space. Okay. Right. So what I want to do for today is basically first talk about the result, which so the part one will be part of a joint work with many people. So Elias Farah, Brad Hart, Ilan Hirschberg, Chris Schaffhauser, Aaron Tikrichis, and myself. So one observation. So yeah, the part one will be about a result that states more or less the following. So these objects, we will see now with some examples, you should think them as sort of bundles over topological, compact topological spaces whose fibers are von Neumann algebras. More or less, that's the idea behind their behavior. And what you can show is that under suitable regularity assumptions, in particular, a sort of McDuff property, a suitable adaptation of McDuff property, this bundle structure really produces some strong transfer of properties from the fibers to the whole structure. Namely, under a McDuffness assumption, you can see that if a property holds on any fiber, which are von Neumann algebra, so we understand well, then you can show it holds everywhere. And so structural properties of tracially complete C-star algebras are heavily influenced by those of von Neumann algebras. And this was a phenomenon which was already observed by other people in classification. There are many ongoing joint works with 5 or more authors on this topic. All of them, regrettably, have not been published yet. It seems to be a common theme here. But they noticed this transfer phenomenon in different situations in a sort of an unorganized way. So what we did was employ model theory to give a more formal definition and sort of isolate this phenomenon better and see to what extent it was holding. So this is part 1, which I think is going to take most of the talk, and part 2 is more of a sort of example, I'd just say, of something, and I'll explain briefly what it is. So almost all things we can do and say about tertially complete C-star algebras, almost all interesting things and interesting definition, we can really make sense of them in the factorial case.
Can I ask, can you spell out what it means, closed face?
Sure. So it is closed as a set. And so T of M is a convex set. So it's a face, which means that whenever you can write down a point, meaning that if tau belongs to X and tau is equal to some convex combination of 2 other elements, then the 2 elements will have to belong to X. But you also want it to be close. Sorry?
I guess when convex is over,
So I'm assuming always unitality here. So as soon as it is closed, it will be compact. That's maybe I misunderstood your question.
No, I mean, you can have a closed subset of the trace space, which is not convex.
Sure, sure. Right. So in this case, if I assume it's a face, it's automatically convex. Yeah. Yeah. So yeah, most interesting things we can do is in this case, to the point that I was wondering whether maybe this is the right definition, this is the right category to consider, because really there is not much we can do when we don't assume factoriality. And the example I will give you, at least from a certain perspective, solves a question which was asked for some time, and tells you that the answer is no, because this class is, for instance, not closed under ultra products. So you can find an ultra product of factorial tertially complete C-star algebras, which is not factorial. So at least from a model theoretic perspective, this class is not axiomatizable, so it's not nice. So you do need to work also with these guys. Now, the name, as you will see from the examples, is related to the fact that these objects, the intuition is that these objects resemble the most factors from von Neumann algebras. I find this intuition very misleading, but the terminology is established now. So we'll keep it this way. So some examples. So the first 2 class of examples are sort of obvious. I already spelled them. Let me write them down. So M tau, where M is a tracial Neumann algebra. And again, I already said this. M tau is factorial. If and only if M is a factor. Second class of example, equally simple, but it shows you how these tertially complete C-star algebras include way more than simple tertial von Neumann algebras and have a very strongly topological flavor, is simply abelian C-star algebras. In this case, unital abelian, of course. In this case, the 2 norm, so I should say with what space, and I can take the whole state space of X, of C of X. So of course, every state on an abelian C-star algebra is a trace. If I took all states, the 2 norm induced by this is just the C-star norm. So obviously being a C-star algebra, the unit ball will be closed. The third class of examples is probably the most useful and most interesting, and it is the way how these objects are related to C-star algebras, which are not necessarily tertially complete, and it is Tracial completions. So this is a definition which was isolated by Ozawa And it goes like this. So let A be a unital C-star algebra with limited trace space. And you can define the completion of A with respect to TA as the set of sequences, bounded sequences in A, which are Cauchy with respect to the two norm induced by the trace space. So is Cauchy. And you mod out by those sequences which are null sequences. So AN is of course, you can do this also for a subset of the trace space. You're just going to have a larger.
So maybe I missed something basic in the first one here. So here you've got a C-star algebra, and then you've got a subset of some special subset of the traces space.
Yeah.
In the top one, there's no X.
So
I guess there's an obvious.
I guess I be precise when X is a singleton. So in this case, X is a singleton, and you can actually show that whenever you have a Tracially complete C-star algebra and the set of traces is a singleton, then that's going to be a von Neumann algebra. And the reason is that you look at the GNS representation, and because tau has to induce a norm, the GNS representation will be injective. And now completeness with respect of the two norm corresponds to strong completeness, because that's what usually happens there. And so you get a von Neumann algebra. So yeah, I didn't write the parentheses, but yeah, it's with a singleton.
And factorial just means it was an extreme trace.
Exactly, exactly. When it's a singleton, it has to be a phase, so it has to be extreme. Right, so this also is factorial because I'm taking everything. And in this case, so this is interesting because now we have the algebra. What's the simplex? So usually we consider ATA with what I'm going to improperly call again TA. So each trace on A can be naturally extended to a trace in the completion, simply being Cauchy sequenced by taking the limit of the values. Now and this is, I guess, the first example where you can see how little we know about this stuff. We do not know whether this operation stabilizes after one step. So if you take the closure of a C-star algebra, you obtain something. If you take the closure of the whole trace space again, does it stay the same thing or you get something larger? In other words, we do not know whether it's always the case that these two things are equal. We don't know. It could be. So this could be. That some traces in A have their canonical extension, which is the one obtained by taking limits, but possibly they have more. And this is sort of annoying. In general, there is what I believe it's in terms of studying structure of Tracially complete C-star algebras, maybe the most daunting and annoying open problem is what Stewart White referred to as the trace space problem or trace problem, which asks the following. So let Mx be a factorial Tracially complete C-star algebra. Is X necessarily equal to the whole trace space? We don't know. We know many examples where this is the case. For instance, in von Neumann algebras. The McDuff situation I was telling you about, to which this result will apply. Again, there's not a published proof, but it seems like it's the case also in that class. But in general, we do not know. And of course, even if this is a smaller, even if it were a smaller subset, it will still be a phase. You can show it's still a phase, so this is still factorial. So answering positively this would also answer this by saying, no, this can never happen. All right, let's see. I wanted to give you two more examples. I'll try to be quick. So this one is not really needed later, but I think it gives a nice idea of how topology and fundamental algebras can merge in this class. So fix a compact Hausdorff space. X and a tracial fundamental algebra N. This again is a definition which was first considered by Ozawa, and is the notion of trivial double U star bundle. We consider the trivial double U star bundle. And again, the first person who isolated and studied this object has been Ozawa, same paper, which is usually denoted with a little sigma there. And you should think them as continuous functions from X to N, except they are required to be continuous with respect of the 2 norm on N, not the C star norm. So this is not exactly the C star tensor product of C of X and N, but it's something slightly larger. It's the completion of that once you put the suitable 2 norm on this. So which is the suitable 2 norm? For every measure in the dual of C of X, you can define a trace on this. So let's call this guy M. Define tau of mu as the integral of f over x of well, tau of f of x, the mu x. So here tau is tau of n, is the trace over n. So f of x gives us a bunch of values over n. We take the trace and we take the integral. So each one of these gives us a trace, and you can see that m with the probability measures over x is Tracially complete, and it is factorial. If and only if n is a factor. So you basically have a situation where x represents the boundary. You have a Bauer simplex, and x represents the boundary of your simplex. All right, so last example, this one we need, and it's the notion of ultrapower. So here we don't even need to start from a Tracially complete C star algebra. So given a C star algebra A and some closed subset of TA, we can define what I shall call a UX, where U, so fix a free ultrafilter on the natural numbers. And we define this as the quotient of L infinity of A, modulo what I'm going to call CU of X. And this is simply the ideal of all sequences, such that the U limit of the norm, of the 2 norm, goes to 0. And you can imagine what's the definition with ultra products. It's similar. Now I need some space. Maybe I can do this. Because again, usually when you have a Tracially complete C star algebra, you identify the algebra, but then you also want to sort of be careful and identify what's the set of traces giving you the norm. And in this case, you can look at all limit traces. So with the node by XU, the set of limit traces on AUX. So they're basically traces of the form tau n with the tau n in X for every n. Now, this set is sequentially closed, but it's not closed in general. So in order to have a nice definition, we take the closure of this, and is usually, so XU would be the closure. It's usually denoted like this. And you can also obtain by taking the ultra coproduct of compact Hausdorff spaces. And we have that AUX XU is tracially complete. Okay, so this was it for examples. Any questions so far? So the proper definition will be a family of subsets of natural numbers, which is closed by intersection and closed by containment. But you should think it as a sort of measure on the natural numbers, which has values 0 and 1, a finitely additive measure. So it basically, what it does is when you have a sequence of real numbers which is bounded, you know it's going to have some convergent subsequence, but you don't know which one is it. The ultrafilter tells you which subsequence you have to look at. Basically, the set of indices of measure 1, you're gonna find one which converges somewhere. So it's a way to find limits when limits do not exist, essentially.
You mentioned also like set or it's common, but also
Sorry?
Those are the function.
Yeah, and it has to be maximal. Yeah, it has to, whenever you partition n, it has to pick one. One of the elements has to be in your ultrafilter.
And free just means not all the subsets they think level.
Exactly.
So it's not your.
Okay.
But this is something I'm never completely clear on. Why do you want just the free ones?
Well, if you don't take a free one, basically it's like taking a limit and looking only at the nth coordinate, so you get A again. You don't get something different.
Okay, okay.
If n is a set, if the singleton n as measure 1, taking this limit, it's like looking only at the coordinate n.
Okay.
And the ultrafilter you can show then is just whatever is in the nth coordinate, which in this case is A. So it's a sort of useless definition.
Oh, yeah, fair enough.
But it makes sense in principle. Okay, so I'm gonna throw in, while I erase the blackboard, some model theory. For those of you who are a bit more familiar with what model theory does, you can find a language which allows you to work with tracially complete C-star algebras. In particular, you should think of the language of von Neumann algebras, which is given by the usual operation plus a 2 norm. And in tracially complete C-star algebras, the 2 norm will be simply interpreted as this new 2 norm. And this notion of ultrapower is the right one, is the one that arises once you consider tracially complete C-star algebras as structures in that language. And you can also show that tracially complete C-star algebras are axiomatizable there. Now, for those of you who are not familiar with model theory, never mind. I mean, it doesn't matter. What I want to do next is set up some definitions to make sense in a formal way of this transfer phenomenon I was referring to at the beginning of the talk. So this definition might not make you happy if you're not used to work with formulas, but bear with me, and I hope I can convince you it's something meaningful. So an AE max formula P of X bar. So we basically want to find a way to talk about general properties without saying what a property really is. We will just define a set of suitable properties to which the transfer phenomenon will apply. So an AE max formula phi of X bar is, let's say, a formal expression in some free non-commuting variables. Free variables of the form and again, just imagine it as a meaningless sequence of symbols that is built following certain rules for now. We start with a supremum over a finite number of other free variables. followed by an infimum, again on some other free variables, and then we plug in a maximum of a bunch of star polynomials evaluated in 2 norm squared. So where Q, well, I should say Qj and max over J, Qj's are star polynomial. Now, this object by its own doesn't have a specific meaning, but it gets a meaning once you interpret it on a Tracially complete C-star algebra. So let me explain. So fix some tuple Mx. Any formula gets interpreted as a function which we denote this way, which goes from M to the R, where R is this number here, into the real numbers, and to each tuple A associate what we call the evaluation of phi on A bar, which is simply defined as supremum and infima now are computed over the unit ball of M. So here, when I say that the tuple, when I say that the tuple has norms smaller than 1, I mean that each coordinate has C-star norm smaller than 1. It's really important to put the C-star norm here. And the rest is interpreted as you might imagine. So now instead of X bar, we put A bar, the other variables ranges here. And the 2 norm is interpreted according to whatever is the 2 norm here. So now this is a real number. And you get a function. In certain cases, it's continuous. In certain cases, it's not. When M is separable, it will be Borel measurable, but we don't care about that. But it is a function. So any question about this definition? Well, usually when you do this operation. No, yeah, you're right. Yes, of course. Yes, sure. Sorry, I was saying something silly. Okay, so let me give you one example, which allows me also to introduce a definition of what a formula like this is. Oops. For every n, we can define phi of what I'm going to call Mn, which has n squared free variables, and basically isolates the notion of the relations of generating a matrix algebra. So it's going to be the maximum. Sorry. Now I don't want to write all of them, but you can imagine. What will be this? I'm going to put dot, and the last one is sort of more important. So here, by dot, I mean all the other relations that matrix units satisfy. So it's not hard to see that if you can find a Tracially complete C-star algebra in the tuple Aij such that this is 0, this is equivalent to saying that Aij generates a unital copy of Mn into M. Now let's add a little bit more spice. So for every Mn natural numbers, we define a formula now, which is this is an AE max formula because we allow also this set of variables to be empty. So when supremum and infima do not appear, it's not a problem. So this allows us to define another AE max formula, which we define as the supremum over M many. So the M here is the number of free variables years. Here an infimum over Xij, well, yeah, Xij, with I and j smaller than n. And the formula we plug in here is the maximum of phi of mn, xij, and also this other relation here, xij, y, h, the commutant. This is simply the commutant. And you can see that if mx is such that theta of mn evaluated at mx is equal to 0. Now notice here, this doesn't have variables, so it's just a number. For every mn, this is equivalent to saying that for every separable subset S of the Tracial ultra power of M obtained by with these two norm, there exists a unital copy of Mn inside this central this commutant of S. And the reason is that we will find up to epsilon some elements which generate something which is going to be closer and closer to matrix algebras and which commute with more and more elements as M grows. So we say that if this is the case, we say that Mx is McDuff. As in the von Neumann algebra world, this definition is exactly McDuffness, the existence of unital copies of matrices in the central sequence algebra when M when M itself is separable, or in general in the commutant of countable subsets of the ultra power. Okay. Okay, I'm finally ready to define the notion I was advertising so much. So a Tracially complete C-star algebra, we say that it has the Tracial transfer property, which I'm going to simply call TTP. If for any AE max formula, and any A bar tuple of the appropriate length in M, let's say in MR, assuming this tuple of free variables as length R, we have that the evaluation of phi at A bar is equal to the supremum over all traces in X of the evaluation of p tau of A bar, which is just the tuple of where p tau is the GNS representation associated to tau, and p tau of a tuple is just the tuple of all images with the representation, on the Tracial von Neumann algebra p tau of M double commutant. So let me give an idea of what this definition means. So imagine that phi has the form infimum x, and then a bunch of polynomials. So qj of x. And these polynomials maybe isolate some properties related to, I don't know, it could be this definition, for instance, can be all sorts of things. And imagine that when you go to von Neumann algebra, for some reason, you know, this evaluation is always 0 because von Neumann algebras are nice. For instance, you could also express that a unitary is an exponential. Although an exponential is not exactly a polynomial, you can approximate that formula. So imagine that for each single fiber, for each single trace, you can show that the value of the formula is 0. Then the Tracial transfer allows you to say that there is a witness on the whole tracially complete C-star algebra that also satisfies that property. So it allows you to go from local, from saying that a property is true on each single fiber, to global, saying that the property holds everywhere. This is more or less the idea. And I'm going to add a further definition. So MX, say it's factorial. Factorial has the, well, factorial Tracial transfer property if actually you can check the evaluation only on extreme points of X. So if the evaluation of phi is completely determined by the evaluation on only the traces on the boundary of X, which is effaced by assumption.
Can I ask, I mean, I sort of believe that any property you're interested in can probably correspond to an AE Marx formula.
Yes.
But is there like a precise sense in which that's true? Am I making sense?
So I guess the answer is no. I mean, I don't know. It means depends what you mean.
Yeah, I don't know what I mean.
And most importantly, we will see in a second, I hope, that what you say is true up to some extent, because everything will be ruined by the fact that here we can take infima, but not minima. So you think that you want to say, it's often the case that in von Neumann algebra, certain properties are just satisfied on the nose. You can find, for instance, comparison of projections. You can find polar decompositions. And so you can write those formula in terms of infimum of polynomials. So you know the valuation is 0, but when you go to Tracially complete C-star algebras, you only know that the infimum is 0. You don't know that you exactly satisfy them. So it's not even fully true saying that all these properties can be expressed. You can express approximate version of those, but we'll get back to this later. So one thing I should have said that I didn't, so let me add it here. And this is really extremely relevant for all the work that has been done on this object, is that if A is unital and, well, non-empty trace space, but most importantly, is this stable, then its Tracial completion is McDuff. So anything I will say in the next theorem applies to completions of the stable C-star algebras, which are one of the reasons why this property is so relevant. So the theorem, I should put lots of names. So because an initial version of this theorem was proved by Castillejos, Evington, Tiquishis, White, and Winter. And then we gave a more extended version. So it's the same people of before. Elias Farah, Brad Hart, Ilan Hirschberg, Chris Schaffhauser, Aaron, and myself. And the theorem is the following. Let Mx be, and here is really important to say factorial. As I said at the beginning, pretty much all we can do is always, in this case, factorial Tracially complete C-star algebra, which is McDuff. And here I'm going to leave some space for later. Then Mx has the Tracial transfer property. Moreover, if M is separable in a suitable sense, so in the sense of the two norm, then it has the factorial Tracial transfer property, which again, it's up here. All right, so a few comments. The first comment is that this property is really easy to define, but it's also way stronger than what you need to get this transfer. You can go with something which is slightly weaker, which is called uniform property gamma, which is a sort of, again, analog of property gamma in the Tracial setting, property gamma from von Neumann algebras. But actually, you can show some more parentheses that Tracial transfer property is equivalent to something which is even more technical and long to define, which is called complemented partitions of unity. So this is a type of object which has been introduced about 3-4 years ago in the context of Thomson-Winter conjecture, but have proved to be extremely powerful to perform these local to global arguments. And so let me also justify this. These people essentially proved this theorem in the case where the evaluation was 0. So if it was 0 on this side, then it is 0 on the other side and vice versa. It turns out that when the evaluation is not 0, it's much harder to prove the theorem. And this is what we covered. And what we covered was also this last part, the fact that you can, again, only focus, it's sufficient to focus on factors, on extreme points. So unfortunately, I don't have, oh, well, fortunately, depends, don't have really time to explain the proof, mainly because of the definitions that are required to prove it. But let me wave my hand a little bit. So essentially, the idea is that these definitions here give you the technical tools to perform these gluing arguments. The core idea is that being McDuff allows you to find, at least in the ultra power, elements which on the trace space behave like a partition of units. So when you have an element in a C-star algebra, you can look at the affine function that it defines on the trace space. Having these properties, so having these rich central sequence algebras, allows you to find inside those central sequence algebras elements which behave like partitions of unity on the trace space. And with these partitions of unity, you can glue together these partial solutions that you have on each single fiber to obtain a global solution, and therefore show that those two quantities, this one and this one, are the same. The second part, it's a bit different, and it's really a theorem about von Neumann algebras. So let's say this is 1 and this is 2. And to show too what we did, we simply proved that the supremum over all traces in X of this evaluation here, let me just call it phi tau of p tau a bar, is equal to the supremum over all traces on the boundary of phi tau of p tau a bar. And this is really a theorem about von Neumann algebras. And the idea is essentially when you take a fiber, you get a von Neumann algebra, you have your nice model theoretic structure, but you also have, given the trace, a boundary measure on the trace space that allows to disintegrate the trace. And this integration of a trace induces a disintegration of a von Neumann algebra. You have your usual direct integral theory of von Neumann algebras. And it turns out that for E max formulas, evaluating the formula on the von Neumann algebra or on each factor of the disintegration gives this equality. And this also explains why here we need separability, because this disintegration of von Neumann algebras doesn't really work beyond the separable case. So this is more or less what's happening here. Now I want to try to tell you how one can use this theorem to infer some information about the structure of Tracially complete C-star algebras, which was the original goal. So I'll try to make this quick because I would like also to cover the last part of the talk. So yeah, so let MX be C-star algebra with Tracial transfer. Then you can show, for instance, that it has an approximate version. So we go back to what we were talking about before with Bisham, of all unitaries are exponentials. And why is that? So take a unitary in here, in M, and consider the formula, let's call it phi of u of z, single variable, which says inf of h in M1 z minus, and here I'm going to write down exponential of 2 pi I. And here I really would like to have a self-adjoint element, so I'll put h plus h star over 2. Now, this is not, strictly speaking, an Emacs formula, because this is not a polynomial, but with continuous functional calculus, you can essentially show that if you have TTP will apply also to formulas of this form. And now, well, you exploit TTP. You know that on von Neumann algebras, regardless of what mx, the fiber will always be von Neumann algebras. This formula is always evaluated as 0 because all unitaries are exponentials. And so you conclude that phi of mx of u is equal to 0, which unfortunately, being this an infimum, it's not saying that u itself is an exponential. It's just saying that you can approximate it with exponential arbitrarily well. And similarly, you can get all sorts of approximate polar decomposition, for instance. You can get approximate, I'm going to say approximate real rank 0, but this is debatable, but let's say it's a property that when it's exactly satisfied gives you real rank 0. And for instance, you can also get approximate comparison of projections. And when I say comparison, I should say probably X comparison of projections, in the sense that if tau of P is smaller or equal than tau of Q, but only checking traces in X, which is the one giving the norm, then there exists a contraction in M such that V Q P star minus P is small norm. So for any epsilon, you can find one like this. So we all get a bunch of approximate properties. Now, if you used to work with ultra powers, you might think, well, in ultra powers, those properties should be exact. If I can approximate them on M, better and better, there is a good chance that I can get them exactly on the ultra power. And sometimes this is true, but you can actually ask something a bit more ambitious, namely, if we have a sister algebra M to which this theorem applies, which has the TTP, does the ultra power also has the Tracial transfer property? Now, the problem here goes back to a very basic structural problem, which is this. In order to apply this theorem, we need to know that the ultra power is factorial. So the real question here would be, is the ultra power, or more in general, ultra product of factorial Tracially complete algebras still factorial? So, and what happens is that, at least in the McDuff case, so at least in the situation covered by this theorem, the answer is yes. And this was done by some other people, but very close to that. Basically, what they showed is that from this property, so I should say at least the initials, so this is Carillon, Castillejos, Evington, Gabe, it's Chris Schaffhauser, Aaron, and Stuart White. All right, so Carillon, Castillejos, Evington, Gabe, Schaffhauser, Tiquishis, White. Okay, they proved that starting from approximated versions of this, you get that on MU, you have exact versions of this property. So mu has real rank 0 and XU comparison of projections. But now, so from here, they did a further step. And what you can show is that if your real rank 0, you're generated by projections. And if to distinguish projections, it's enough to look at the traces here, it actually means that this has to be the whole trace space. This is not an obvious argument, but this implies, and again, it's them again, that the trace space of mu is equal to XU, or rather XU is the whole thing. So obviously, mu is factorial because this is everything, so it's a face. And so now you can show that it has CPU, and in particular that mu XU has the Tracial transfer property. And so, for instance, you get that all unitaries are exponentials in the ultra power. You get exact polar decomposition in the ultra powers. In particular, you get stable rank 1 in the ultra power, and all properties that you usually have in fundamental algebras. Because in ultra powers, infima become minimum because of the usual diagonalization argument, Kirchberg epsilon test, saturation, whatever you want to call it. All right. And I will say something more, again, more unpublished work, mainly by these people who showed that actually you can get comparison also in the algebra, in any McDuff-Sister algebra. You don't need to go to the ultra power. If you work hard enough, you get exact comparison as soon as you have a Tracial transfer property. And Evington, so I'm going to just write this. Sam managed to show that if mx is factorial, so using this comparison, if is factorial plus McDuff, then the trace problem has positive answer. Then E of m is equal to x. All right, so I'll try to be super quick, and in the last few minutes, I'll show you that the answer to this question is, at least with ultra products, no. Okay, so no, I'd like to give this example because I think there is at least one person in the audience who will be familiar with the objects I will use. So yeah. So I'm going to work with homogeneous sister algebra. So a sister algebra is n homogeneous if all irreducible representations have dimension n. And so remember when at the beginning I gave examples, I told you when you have a billion sister algebras, the 2 norm and the C-star norm are equal. On homogeneous sister algebra, actually in sub-homogeneous sister algebras, they don't have to be equal, but they will be equivalent. So in this case, let's say A is unital, so the spectrum is compact. A unital. What you can show is that the 2 norm induced by the whole trace space of A, which is always smaller than the C-star norm, is actually greater than the C-star norm, I think 1 over square root of n. This is not too hard to believe, right? This is just the supremum over all irreducible representations, but each one of that is a matrix, so you can find a trace there where this relation happens. All right, so if, say, AN is a sequence of 2 homogeneous sister algebra, then the tracial ultra product that we get, which is usually denoted like this, and in this case, the space, the ultra coproduct has this funky notation here, but as a set, this is actually the C-star norm ultra product where usually the U goes below, where here is just the direct product of an modulo C0, U. So you take all C star normal sequences. And the reason for that is that these two norms are equivalent. And also you can show, so also the two norm induced by this is equivalent to the C star norm in the ultra power. Now, it's almost over, I swear. I apologize for, yeah. All right, so that's the premise. Who are the AN that we're gonna take? So there is these examples from Pedersen and Petersen. So they managed for every n, there exists AN at two homogeneous unital C-star algebra, which they are algebras of continuous sections. I will just say this, continuous sections on the n-dimensional convex projective plane with fiber M2, with fiber isomorphic to M2. I will not say more, such that there exists a guy which is a linear combination of commutants. So you can write it down as linear combination of commutants. So in particular, it annihilates all traces, but Z is never equal to X if X is a linear combination of at most n commutants. So you know you need some, but you need more than n. That's what they proved. And actually, this was refined by Tristan and Ilias in saying that you can show that actually Z minus X has to be greater than 1. So they're bounded in norm for any of this. So same thing. They're not only different, but they're far away from those. And the core reason for this is a theorem called, I think, Borok-Coulomb's theorem that says that when you have a continuous map between two spheres, which maps antipodal points to antipodal points, then the dimension of the target has to be greater than the dimension of the domain. So if you can show that this is smaller than 1 and X is smaller than n, you can basically build a map which violates that theorem. But again, short on time, I will not say more. So, okay, let's call this Zn, since we're gonna take one for each n. And we look at the ultra product of these Pedersen's algebra and take Z to be the sequence generated by these elements. Now Z witnesses something. Since Z exists, we know that the trace space, let's call this guy M. The trace space of M is strictly bigger than the closure of the limit traces. Why is that? Well, Z annihilates all limit traces because each coordinate is just a sum of commutants. So it annihilates all limit traces. But at the same time, it cannot be itself approximated by linear combination of commutants because of this condition here. And since if an element annihilates all traces, it has to be approximated by linear combination of commutants. This means that these two guys have to be different. All right. Now suppose, remember what we wanted to prove. We want to show that this is not factorial. Now, of course, all of these are factorial because of what I basically said here, because the C star norm and the two norm are equivalent. So they are closed. So why is not factorial? Suppose that this is a face. Then this is standard theory on convex set. There exists a continuous affine function with positive values on, well, the trace space of n, such that it annihilates all limit traces. But for instance, it has value 1 on some sigma, which is not in that phase. And this is a problem, and I'm going to be done after this. So here we need to use a result by Kuntz and Pedersen, which is really classic. It's almost folklore at this point. So Kuntz, Pedersen tell us that there exists a self-adjoint A in M such that A hat is equal to F, where A hat is simply the evaluation function on traces. But we can do more. We can find A such that, moreover, A is not positive, but for any epsilon, it does its best. So A lies between epsilon and the norm of F, more or less. So now we look at A plus epsilon, which is positive, so has this form. And on the one hand, we have that the 2 norm of B star B on limit traces is very small. Because remember, A was 0, since F was 0 on this. B star B is just an approximation. So this is essentially, I'll say, almost epsilon. Probably you need put some constants there. But also remember that the C star norm was equivalent. So this is smaller than n times this. Or again, this was square root of 2 probably, since they are 2 homogeneous. So the norm of B star B is small, but at the same time, the evaluation of B star B on the trace sigma has to be big. And that's a contradiction. So sigma of B star B is close to 1, but at the same time, it has to be bounded by B star B norm, which we said was smaller than something related to epsilon. So for epsilon small enough, this is a contradiction. So apologies, I went over time. Oh yes, apologies. That's all I want to say. Thank you.
Thank you for the result.
Over time. Do we have any questions in the audience? Or online?
With some very elementary questions. What do you mean by a continuous section on CPN?
What do I mean by? Oh, okay. So basically, yeah.
What's the bundle? I'm asking.
So the bundle, okay. So a point in here, and then the fibers. There is basically a 4-dimensional complex vector space where 2 coordinates can be anything you want, and the other 2 coordinates have to be points belonging to the elements from the base space. So let me write it down, maybe. Chalk. So you have I should probably, yeah, let's say X, and you get a matrix A, D, and let's say B tilde and C tilde, and it's something like that. A and D are just complex numbers, and B tilde belongs to X, and C tilde, you want the adjoint of C tilde to belong to X.
Not free, sorry.
You by free you mean trivial? That yeah, no, it's absolutely non-trivial. Yes, it's very.
Does it admit an action like a SU1?
I have no idea. No, it's a very twisted bundle. Yes, it is very twisted. In fact, the thing I'm trying to work on now with no success At the beginning, I gave you the definition of trivial double star bundle is the ultra product of those factorial. Maybe yes, maybe no.
It's funny to mention when it's natural, then I mean CPN can be understood as a homogeneous space with SUN over UN -1.
Right.
And then to every representation of UN -1, you have a corresponding homogeneous vector bundle it's an action. So maybe it's the
Yeah, I haven't thought about it. I don't know.
sorry, I'm just trying to make it look like something I understand.
Sure. No, I'm 90% sure the definition is this one. I checked it a few days ago, but in any case, you have two coordinates that do whatever they want and two coordinates that depend on the point. They're basically,
Later on.
you have some identification of X, of the points in X with complex numbers. And so that's how you make sense of a matrix here.
No, I was going to go on.
Okay, no, I was just gonna say this. Maybe it weird in the sense that, I don't know, usually when you get secret algebras, they can be twisted in the sense of take some continuous math from some space to n, and then look at a projection of, I don't know, rank n of 2 or something everywhere, and that will somehow twist the, you just look at the, section which, the corner that you get from that projection.
Yeah.
But this is in fact so twisted that it doesn't matter how big you make your mn, and you'll never be able to find projections which you can cut down. It's sort of the multiplication is somehow. It's very weird.
But it's a projected mod. I mean, the sections are a projected mod.
They're just sections, but you also have to multiply these sections as well. So,
That's kind of okay.
yeah.
So yeah. So here I should have said a subset of continuous section, which has all the C-star algebraic properties. So yeah, the multiplication is defined essentially in reasonable way, adjoint in the reasonable way. But it turns out to be extremely twisted. And in fact, it's not the whole set of continuous section. I should have said subset of a certain subset, a special subset. It's like writing with glass. All right.
And then the very elementary question. So what these n-homogeneous C-star algebras, I mean, are they common?
So
Or is it quite restrictive?
So back in the days, I think they were studied more in the 60s and 70s in the framework of type 1 C-star algebras. Like for instance, classification program deals with simple C-star algebras with Z-stable, which are basically at the opposite side of the spectrum of this. They have a very nice representation theory. I think nowadays they're a bit overlooked because they were studied a lot in the past. And the canonical example is continuous functions from some compact Hausdorff space into M2. That's one. Then you take subalgebras of those and you can get twisted stuff. So non-trivial ones. So for instance, that's another example, which I didn't define, but looking at subalgebras of those, you can get as twisted as you want, basically. But I'd say at this point, so there is a whole theory which was developed, I say in the 60s and 70s about these things. And bundle algebras in general.
Thanks.
Yeah, no problem.
I know you started out by saying not much is known about the structure of these tracially complete C-star algebras, but do you know, is there a notion of the Kuhn semigroup of these guys?
So at least in the McDuff case, there is a hope they are real rank 0. So maybe whatever actually think there might be some known things on the K0, but I would say that in that setting, they look more like von Neumann algebras than C-star algebras. So you should probably focus on projections, but this is in the McDuff case. In the general case, I really don't know.
Yeah, I mean, I'm just even wondering, like, whether you'd want your Kuhn's approximations to be in the C-star norm.
Yeah, okay.
Norm, I don't even.
Yeah, right. If you take the canonical Kuhn's semigroup and apply it there, you will get something which is terribly big because these are non-separable C-star algebras.
Yeah, right.
So if you want something that maybe resembles something built from something separable, then you would like to take something with respect to the 2 norm.
Yeah.
That's a thing. I don't know. But yeah, if you just take them as C-star algebra with the C-star norm, they're terribly big. Like von Neumann, it's like considering von Neumann algebras with the C-star norm. They're terribly big. Yeah, I don't know.
Yeah, fair enough.
So yeah, I was curious about the thing you said at the start about like the first open problem was just if factorial the complete C-star algebras is whether the selected traces actually have to be all traces. Right? Yeah. Has anyone got anything to say about that at all? Or
I think so the best we have right now is this, which again, unpublished, but I trust Sam. It definitely he didn't show me the proof, but the thing he said makes sense. And in general, I think you can agree that if you have comparison of projection looking at a subset of traces, it sort of hints that that should be the whole set of traces, because otherwise projection should detect it, especially when you have so many projections like in the McDuff case. So in the amenable situation, it should be covered. In the non-amenable, I've been thinking about this a lot, and the best I could get was that for ultra power it's a bit easier. But now the problem is that for ultra power you don't know when they're factorial. So you get a result saying, oh, when an ultra power is factorial, and for instance you have W star bundle which are trivial, then I almost proved that it's always the case that the trace space is the whole thing. But no, in general, very little is known. And yeah, the problem is that this question has been around for a long time, but not many people know it because it has not been published anywhere. But also the one of ultra products.
I'm not familiar with McDuff, but I don't know. Just for example, could a originally finite dimensional C-star algebra is that all McDuff? So this theorem of Eddington would apply? Or?
I'm not sure.
What's McDuff again? Is it easy to explain?
That you have these copies of matrix algebras inside the central sequence algebra of the ultra power. So you basically want to have approximately commuting copies or approximate copies of matrices. Like in Von Neumann algebras will be absorbing R more or less, absorbing the hyperfinite to one factor. And yeah.
That's the C-star version of McDuff.
Exactly.
It just feels like you should be able to just play around with, I don't know, sequences or you know, of different sized matrix algebras and things, or something should come out, but maybe not. Like just to get a counterexample, I mean.
Well, the counterexample cannot be McDuff. His Sam is correct.
Right. So yeah, I have to understand what McDuff really means. Okay.
From the audience or online, they could actually see the talk. It's not clear. Okay, if not, let's thank Andrea again for a very nice talk. And next week our talk will be only online, and it will be Therese Bassa-Landry, who will talk about developments in non-commutative fractal geometry.